This is a short description of an ultrasonic sensor. Our project objective was to determine and evaluate the static sensitivity and dynamic response of an ultrasonic sensor through various distance measurement and analysis. The physics of operation of the sensor deals with sending an ultrasonic signal, which is a high-frequency sound wave, towards an object. That signal bounces off the object and reflects back to the sensor. Based on the time that it takes for this to occur, the sensor will output a voltage. Our sensor was set up with a MIDAC. We connected the analog pin to the analog output on the MIDAC and used the 5 volts power supply in the MIDAC to power the sensor. Here's a short video of our static calibration. We took measurements every 3 inches from 10 to 40 inches. We found a linear relationship and used a linear regression to obtain the slope of this relationship, which we could then translate into the static sensitivity. Here are our tabulated static sensitivity values for the dull and shiny plate, as well as the nominal value given on the datasheet. Here's a video of our dynamic calibration. We had 2 plates in line and quickly removed the front plate to generate a step response, as seen in the LabVIEW VI. Here are 2 of the step responses for the shiny plate. We also performed a ramp response in which we moved the plate from in front of the sensor back at a constant rate. We found the linear relationship, and we also found the update time for the sensor based on the size of the staircase steps. Here are those values tabulated. The update time experimentally was 89 milliseconds, and given in the data sheet it was 50 milliseconds. We also did an uncertainty analysis in which hysteresis error dominated. We found that the shiny plate had the lower uncertainty out of the 2 plates tested. As far as analysis goes, we found that the static sensitivity of the dull and shiny plate were both within range of the nominal value of 9.8 millivolts. However, the shiny plate had a static sensitivity closer to the nominal value. We had a relatively low overall uncertainty, and hysteresis error dominated that uncertainty. Our combination of a very low time constant from the step input and a linear response of the ramp input suggested that the system behaves as a 0th order system. We would recommend this sensor for taking measurements in the range of 10 to 40 inches. Beyond 40 inches, we ran into issues with an oscillating signal. The linear nature of the signal makes data gathering and analysis very straightforward. And at $20, it is an affordable option for automating your measurement needs. So we recommend this sensor as a great option for taking measurements. Thank you.